Hello student, welcome to our physics discussion, that is physics in a smart way. In our last video, we were in step 5 of isothermal or constant temperature process. Now step 5, I think that is step 5 or step 6. Step 5 was the graph. Step 6 it should be, that should be number 6 of the, just let me correct it, of isothermal process, because step 5 was graph, as I remember. Okay, no time to go back to that now. That is practicality of isothermal process. Of course, I have not talked with you. Here, practically means how an isothermal process should be executed. Actually, should be done in the practical sense. Let us say we got a cylinder of ours. Cylinder contains an ideal gas molecules you see. And initially, the gas was at a pressure P1, volume V1, and temperature T1. Let us say these things we know or we have measured it, we have found it correctly. There is a piston, a tight-fitting piston. We have put some weight. Let us say weight is W1 on the piston. So thereby, we do know the piston will be pushing in the gas initially when we put down the weight. Now, in our case, we are considering the case where already the weight is there for some time, a good amount of time. So weight W1 is there. So thereby, the piston is at rest. The gas is in a state that is known as equilibrium state. Gas is in a state that is known as equilibrium state. Sometimes our books, they confuse us using the words maybe quasi-static process, sometimes reversible process, sometimes irreversible process, and these things are not known to us usually. We are not very clear on them. Okay. So the words like, just like I have told you, equilibrium state, quasi-static process, reversible process, irreversible process, until unless we understand them, they remain as Denis the menace. They remain as a zombie who are intended to make threat to us every time. Okay, so let us try to understand them. That is the theoretical. So this is the gas. Gas has got piston. Gas is confined on one side by the piston, or the three sides by the walls of the cylinder. The wall of the cylinder may be metallic, maybe non-metallic, doesn't matter. Beyond the wall, the thing that remains is the surrounding. In our case, normally that is air in our laboratory. So this is surrounding, and that is the system of ours. When we see that we have put a weight W1 on the piston, and a long time has passed, piston is not seeming to move, already that might show some displacement and all those things, we do not know, nor we are interested to know. So thereby the piston is comfortably at rest, sitting just like Gautam Buddha or a monk. So thereby that is, the piston is with a pressure, the gas is at a pressure P1 and volume V1 and temperature T1, as you say. That is known as an equilibrium state. The gas is in equilibrium with the surrounding. The gas is with a with a pressure P1, volume V1, and temperature of the gas T1. That we did measure, or we could find to know. Okay, so that pressure P1, volume V1, and temperature T1, if somebody refers that, or if somebody points out that, if somebody draws that in the pressure volume graph or in the suitable graph where pressure is P1 and volume is V1 and temperature is T1, let us say the point is T, the point is here, and that is the state 1. We can say the gas was in state 1. The entire state is reduced to a point here. But we do a mischief here. What we do? In addition to weight, we can put some extra weight W2 suddenly on the piston. We put a weight W2 on the piston, immediately we know piston will be going down. Piston will be going down, and finally piston will be coming to a position like this. And before coming to that final, maybe the gas will be going through some vibration and all that. But if you allow a long time to pass, finally the gas is coming to a state like this. When the gas finally has come to a state like this, where the gas pressure is P2, volume is V2, and temperature is T2, maybe there is some heat exchange or energy exchange through the wall of the container that we do not want to poke into. So thereby we know we have achieved, we have arrived at another equilibrium state, that is pressure P2, volume V2, and temperature T2, that in our indicator diagram, that in our PV graph, pressure volume graph is shown by this. But trying to see, the gas changes its state from pressure P1, volume V1 to temperature T1 to pressure P2, volume V2, temperature T2. So thereby pressure P1, volume V1, temperature T1, pressure P2, volume V2, temperature T2. But in which way? I have shown two or three lines, two lines between the, so to say, point 1 to point 2, but we cannot say the gas is going by which way. Gas is going by which way? Okay, because the moment I draw a path, every path is consisting of several points, many points, and all the points, we know they have got their x and y coordinates, means pressure and volume values. So once you draw a path, you know, you have to know about the pressure and volume of the x and y coordinate of all the points on that path. And when we put down the weight W2 and just release the gas, we do not know which are the stages of the process or the pressures the gas goes through. When the weight changes from W1 to W2, how the gas changes its pressure from P1 to P2. We know that gas changes its pressure from P1 to P2, but which way or which path? So thereby, whether the gas is going via this path or this path or this path, that is not definite. That is known as irreversible. It is a irreversible process. Irreversible process. So for irreversible process, you know, process is nothing but a path in pressure volume graph or in thermodynamic graph. So a process is a path. But once you draw the process, then you know you have to then you know that you know about any point on the process, any point on the path. You have to find out, you know about the pressure and volume value and temperature value of any point or any state, because the process goes through some states. When the state of the gas changes, the process is, I think I am clear. So this type of thing, which will be the path of a irreversible process. So for a irreversible process, we can say we know the initial state, we know the final state, but via which path, via which process that goes from first state to second state, P1, V1, T1 to P2, V2, T2, we have not confirmed that. We got no way to find out. So that's a irreversible process. But once you say that you know about the path between point 1 and point 2, let us say, if I claim yes, I know the path between point 1 to point 2, then, and you draw the path boldly and you claim that you have drawn it, then you know about pressure and volume volume values of any point of the path or any process, any state that the gas is going through. You know, a path is consisting of many points. So that has to be done in a way like this. That is a reversible process. That is not an irreversible process. That's a process where you know about the state of the gas anywhere, starting from P1, starting from two end states, or starting from two equilibrium processes, P1, B1, T1 to B2, B2, T2, and how that is done in infinitely small steps. Infinitely small steps. In infinitely small steps. Okay. If it is a reversible, if it is a isothermal process, the walls must be conducting. So what we do? Initially, the weight on the piston was W1. Finally, the weight on the piston is W2. We first find the difference, W1 difference W2 or W2 difference W1. So that difference of material, you have to break it down into very small pieces, maybe the grains of sand, very small. If W2 equal to 10 kg, W1 equal to 8 kg, so difference equal 2 kg. So that 2 kg you do not bring in terms of weight, but you bring in terms of grains of sand or something like that, powder like that. You just put 1 grain of sand just after W1 or when you see the first equilibrium state, P1, B1, T1, you put the first grain of sand. So thereby pressure changes by a very small amount, volume changes by a very small amount, the piston moves by such a small amount that it is very difficult to see, and the temperature changes. If it is to be isothermal process, then you know that because you have gone for compression, a small amount of heat is to be developed. So we allow that heat to be passed out. We are sufficiently patient. The fast grain of sand doing the mischief, doing the job. So when you allow the temperature to be settled up, when you allow the system surrounding temperature to be same, then you put down the second grain of sand. So thereby what you do, by putting the grain of sand one by one by one by one, you make the gap and sufficient time interval in between the you are putting up the grain of the sand so that the temperature and thermal energy takes time to be balanced, take times to be transferred. So thereby what we do, we go through some steps which are very close to each other, and every step we know the pressure and volume and temperature value. So if the process is like this, then the graph can be done. If the graph can be done, then the gas can also be brought down from P2, B2, T2 to P1, B1, T1 by taking up the grains of sand one by one line. So that is known as a reversible process. That is known as a reversible process. All the processes that you are going through, that you are being fed at this stage, they are reversible processes. We do not take irreversible processes because signs of them do not exist usually, because the graph of their path or graph doesn't exist. Okay. So as I told you, and a reversible process should be executed in infinitely small steps with sufficient time gap in between. Or to make my point more clear, if the process is isothermal process, a reversible isothermal process should be done in a way where the system and surrounding, they have got a perfectly conducting one, so that heat can be transferred, and the process should be done in such a slow way, infinitely in infinitely small steps with sufficient time gap in between, so that heat has got time to be transferred within the system surrounding. If during our small steps there is an imbalance of heat, there is an imbalance of thermal energy, and there is an imbalance of temperature between the system surrounding, and that temperature difference should be covered because our process is isothermal process. Otherwise, it cannot be a truly isothermal process. So then, because the infinitely small steps, very slowly, then the process is known as a quasi-static process. A quasi-static process is a almost static process. Static process means a process which is still, which is not a process at all. So thereby the process is so slow that resembles as it's a starting process. It is very difficult to discern. So those processes are known as quasi-static process also. So once you know all those things, these bombastic uses of these bombastic words will be of no use. So an isothermal process should be a very slow one, a reversible isothermal process, and that must be done in infinitely small steps with sufficient time gap in between, so as to allow the heat to be transferred. Let me clear it. But don't think these words isothermal and all those things, they are confined to thermodynamics. Isothermal, constant pressure, constant volume, they are not confined only to thermodynamics. Let us say we consider a issue, we consider a bar or a wire. Bar or a wire. Well, it's not so thick as I am trying it. Where it's fixed between two supports. What do? We take the two ends of the wire, two supports, then slowly move them away. Slowly, mark my words, in infinitely small steps. So when the supports slowly start to move away, we know the wire starts to extend, wire starts to expand. Okay, but that expands, and during this process, we know people usually, or people who are involved in the science and all that, they try to think of the wire in terms of slices. You can visualize the wire in terms of slices, and when the wire expands, that is rubbing between the slices of the wire, and this rubbing creates heat. So if that creates heat, you are doing it so slowly that heat is getting time to getting transferred. But in contrast, if you suddenly pull the ends, then whatever heat that is developed won't be getting any time to be transferred. So if you expand the wire, very, very slowly and allow the heat to be transferred, and in infinitely small steps, then we have gone through an isothermal extension of the wire. Isothermal extension of the wire. So don't think this isothermal, adiabatic, and all those things, they are confined to only thermodynamics. They can be used anywhere, and they also can be studied from thermodynamic point of view. Okay, so that is our idea of isothermal process. And process which is isothermal means the cylinders are perfectly conducting, and the process is done in very small steps, and in a PV diagram, pressure volume diagram, as I have shown you, that is usually because y is proportional to 1 by x, t is proportional to 1 by v. The graph is a straight line that is like this. That is a rectangular hyperbola. Usually, if you use mathematical parlance, mathematical term, so we'll be going through that. In due time, we will deal with the case. But for the time being, that is over.